Okay, so let's come back to our lecture. Okay, so now last lecture, we have been starting to talk about higher order, the higher order linear and so higher order equations. Okay, so we have been talking about, okay, so we have been talking about higher order equations. Okay, so we've been talking about higher order equations, and at that time, okay, so we have been kind of studying the basic theory for higher order equations. So a higher order equation has the form an of t, right? So yn's derivative plus an minus 1 of t of yn minus 1's derivative plus dot 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 plus a1 of t of y prime plus a0 of t of y is equal to b of t, right? So that's a higher order linear equation. And you would like to consider its complementary equation. So that's an of t yc to the derivative of n plus an minus 1 of t yc of the n minus 1's derivative plus a1 of t yc prime plus a0 of t of yc is equal to 0, right? So you consider such homogeneous equation. And then you're going to represent the yc by c1 y1 of t. Okay, so plus dot 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 plus cn yn of t, right? So that's linear combinations of these fundamental solutions. And we've been talking about the Wronskian. So w, y1, y2 until you reach yn, right? So this Wronskian has to be equal to the determinant of this matrix y1 up to yn, and then y1 prime up to yn prime, and dot 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 y1 n minus 1's derivative, dot 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 yn n minus 1's derivative, right? So the determinant has to be non-zero in order to reach a set of fundamental solutions. Okay, so the set of fundamental solutions. And with these fundamental solutions, we've been talking about linearly independency, right? So and linearly independence of a family of functions. So basically, it says that if summation ki fi of t, where I is 1 to n is equal to 0, implies each of the k1 equal to kn is equal to 0, then we're going to say you have linearly independency. And this is the same thing as saying that the Wronskian is non-zero if you replace the y's by f. Right, so that's what happens to the previous lecture. Okay, so now you can see that for homogeneous equations, the key point is to find those fundamental solutions. Right, so in order to actually solve the homogeneous equations, the key point is how do you find this set of fundamental solutions. Right, so and in our second order equation case, we've been finding these fundamental solutions by characteristics, right? So that's a characteristic equation. So we've been finding these fundamental solutions by the so-called characteristic equations, right? So the characteristic equations are the key points, right? So characteristic equations are the key points, right? So therefore, we want to have a similar theory for higher order equations. Okay, so that's the topic of today's lecture. Is that we want to find, okay, so we want to find higher order homogeneous equations by characteristics. Okay, so that's the idea. Okay, so therefore, let's look at the lecture. Okay, so for higher order homogeneous equation, we want to deal with constant coefficient equations. Okay, so constant coefficient equation is going to look like an of yn's derivative plus an minus 1 of yn minus 1's derivative plus dot 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 plus a1 of y prime plus a0 of y, right? So that's equal to 0. So that's a homogeneous equation with constant coefficients, and the leading coefficient is not equal to 0, right? So that's what you would like to have in this scenario. And then you're going to turn this equation in standard form, right? So remember, the standard form is an equation that has coefficient 1 in front of the highest derivative. So that's yn plus an minus 1 divided by an of yn minus 1 plus dot 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 plus a1 divided by an of y prime plus a0 divided by an of y is equal to 0. So that's kind of the standard form in terms of this homogeneous equations. Okay, so in terms of this homogeneous equations. Okay, so that's characteristic equation is just inherits. Okay, so similar as before, right? So the characteristic equation, right? So characteristic equation just inherits those parameters, right? So it just inherits those coefficients. You just pass these coefficients to the equation, and you're going to replace any of these derivatives by polynomial powers, right? So think of the second order equation case. Okay, so think of the second order equation case when we have this equation when it was looking like ay double prime plus by prime plus cy is equal to 0, the characteristic equation is ar squared plus br plus c is equal to 0. And similarly for here, we're going to have an r to the power of n plus an minus 1 r to the power of n minus 1 plus dot dot plus a1 of r plus a0 is equal to 0. So that's going to be the how the characteristic equation is going to look like, right? So and in our previous theory, it was we have been talking about 3 cases. So basically from the characteristic equation, okay, so from the characteristic equation, you're able to solve for the R1 and R2. They're based on the discriminant formula. So minus b plus minus b squared minus 4ac divided by 2 times a. And based on that, we've been discussing 3 different cases, right? So there's a real distinct root case, right? So a real repeated root case, right? So and the complex root case is a good favorite, right? So we've been studying like the 3 different cases, and in the 3 different cases, you're going to have different formulas for the fundamental solutions. So what happens to this characteristic equation, right? So suppose the characteristic equation is having the form, okay? So it's having the form of an nth order polynomial equation. Then you're going to have several different scenarios, right? So the scenario 1 is that you're going to have real non-repeated root. So what does it mean, real non-repeated root? It means that it is going to be a real root, and it is not going to be the single root, right? So that you're not going to have a double root situation. Okay, so this root is not going to be repeated. So that's why we call it a real non-repeated root, right? So in that case, so that basically we're saying that if you have, okay, so case one, let's say real, okay, so real non-repeated root, right? So if you have this case, then you're going to correspond to, let's say, R of S, right? So that's presumably there should be, okay, so presumably there should be n different solutions to this polynomial equation. This is what we call fundamental theorem of algebra, right? So that basically you say that by fundamental theorem, okay, so right? So by fundamental theorem of algebra, right? By fundamental theorem of algebra, you're going to see R1, R2, dot, 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 Rn. There are going to be n solutions that are in the complex, that are complex solutions. Is that good, February? However, some of them might be repeated. That means maybe Ri is equal to Rj. They're repeated. But if you have a non-repeated root case, then your corresponding fundamental solution is going to be just raising this non-repeated root to an exponential. And however, you might have some other cases, right? So let's say case 2, right? So the case 2 is that, let's say, suppose you have complex non-repeated roots. So if there are complex non-repeated roots, okay, so if there are complex non-repeated roots, they must be conjugate. So because the fundamental theorem of algebra says that if you have a polynomial equation with real coefficients of order n, then there are n roots counting, and in the set of complex numbers counting multiplicity. And if some of these roots are complex, then they are complex conjugate pairs. So that means you're going to have Rj, but you're also going to have Rk, right? So let's say Rj, Rk is equal to, let's say, lambda plus minus I times mu. So if one root is complex, okay, so it has a non-zero imaginary part. So that means it is complex. If one root is complex, then its complex conjugacy is also a root. So that's going to be the scenario. Okay, so that's going to be the scenario. Now, if that is the case, then the solutions are constructed as we said that the real part enters the exponential and complex part should enter sine and cosine. So that means if you're going to create two different solutions, yj of t is equal to e to the power of lambda t cosinesis of mu t, and yk of t is equal to e to the power of lambda t sinuses of mu t. So that's going to be your complex conjugate case. Okay, so complex conjugate case. However, the other case, okay, so let's say case 3. Case 3 is going to be kind of completely new. Okay, so from what you learned before. Okay, so therefore that means you're going to have real repeated roots. Okay, so I mean it might not be even real repeated root, right? So why? Because you have a polynomial equation. It might happen that even the complex roots are conjugate, but they are also repeated. So there are several complex roots that are same to each other. Correspondingly, there are several conjugates are corresponding to each other. So that maybe we'll say complex roots. Let's say repeated roots. Okay, so maybe we'll say repeated roots. Okay, so what happens to the case of repeated roots, right? So if you are in the case of repeated roots, then it's we're saying that if the roots are repeated k times, we're going to first obtain the basic solution from either case 1 or case 2. So that means these repeated roots might be, okay, so it might be real, it might be complex. So it's not kind of guaranteed because you're a higher order situation. In a second order situation, if the roots are repeated, they must be real. But in our case, if they're repeated, they might even be complex. But let's say if you have a repeated roots, then what happened here is that if the repeated roots are real, you're going to first construct the exponential. If they are complex, you're first going to construct e to the power of the real and then sine and cosine. You construct these solutions. But as long as you're constructing the solutions, this is going to just count for one repetition of that solution. You're still lacking a lot of other solutions because the solution is being repeated. So basically, it says R is, let's say, repeated. Okay, so suppose the root R is repeated. Okay, so that let's say k times. And first you construct the solution, let's say yr of t. Then what you're going to do? Well, there are going to be R, right? So you're going to have k such solutions, k such roots. So you're lacking like k minus 1 solutions. You just created one solution that is yr of t. So what about this one? Well, for this one, you're going to use the golden principle, t times yr of t. And then you continue doing that. This is going to raise until t to the power of k minus 1, yr of t. So that's going to be the situation. So do not hesitate to multiply by t's because we're going to use the golden principle. Okay, so that we're going to use the golden principle. So that's going to be the scenario. So this is going to be the principle here. It says that you first obtain the basic solution from either case 1 or case 2. Okay, so as long as you constructed this solution, you're going to kind of multiply the basic solution by t to the power of square and until t to the power of k minus 1. So that means the repetition is k times. Just multiply until t to the power of k minus 1 to obtain the additional solutions from the repeated roots. So that's going to be your scenario. Okay, so that's going to be your scenario. So do not hesitate to multiply by t's, and you can actually multiply a lot of them. Okay, so until you have satisfactory of the number of solutions. If the solution is repeated k times, then you have to keep multiplying by t until you get k such fundamental solutions. Is a good family. Okay, so according to these three cases, you can see that for each of these rules, right? So let's say the characteristic equation, right? So suppose you have the characteristic equation an r to the power of n plus an minus 1 r to the power of n minus 1 plus plus a1 of r plus a0 is equal to 0. You have this equation, then you're going to have solutions r1 up to rn. They're going to be complex solutions. Now you can see that for real solutions, right? So they might be complex, includes real numbers. You have constructed one solution. For two different conjugate complex solutions, you construct two solutions. If the solution is a repeated k time, you construct k solutions. So that means in the end, you're going to have just n solutions, exactly n solutions. The order of the equation is n, you have n solutions. And these solutions are fundamental solutions. Okay, so these solutions are fundamental solutions. So therefore, the general solution, right? So the general solution, according to our theory, is just given by y of t is c1 y1 of t plus c2 y2 of t, right? So plus dot 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 plus cn yn of t. So they're just linear combinations of those fundamental solutions. That's it. Is that good, family? Okay, so that's we're going to reach such a theorem. Okay, so the general solution is just the linear combinations of those fundamental solutions. And in order to have particular solutions, what you just have to do, okay, so what you just have to do is to find those coefficients by initial conditions. Is that good, family? Okay, so by initial conditions. And in general, what kind of initial conditions should you have? Well, you should have an initial condition, right? So if your equation, let's say, if your equation isyn's derivative, let's say an plus an minus 1, yn minus 1's derivative plus dot 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 plus a1 of y prime plus a0 of y, let's say is equal to 0, what kind of initial condition you should have? Well, you should have y of 0 is equal to y0, and y prime of 0 is equal to y0 prime, right? So dot dot dot, what you should have in the end? Well, you have n minus 1's derivative of 0 is equal to y0 n minus 1. Some people is going to ask me, why is yn? Well, it's not the case. Remember, if you have second order equations, right? So remember, if it is y double prime, by prime plus c of y is equal to 0, then you're going to have the initial conditions y0 and y prime of 0 is equal to y0 prime. You're not going to have y double prime because your y double prime can be solved from y and y prime. So that's the same situation for nth order equation. The initial conditions is going to start from the initial value until you exhaust to the n minus 1's derivative. And from which you're able to solve this coefficient c's and get a particular solution. Is that good for everybody? Okay, so that's kind of the procedure, how you solve this homogeneous higher order equations. Okay, so let's do some exercises. Okay, so what about this one? Says that, can you find a general solution of this equation? Okay, so fourth derivative. Okay, so let's say y fourth derivative plus 5 times y. Okay, so second derivative plus 4 times y is equal to 0, right? So we just want to find a general solution. Okay, so how are we going to do that? Well, it's kind of simple exercise, right? So it's kind of simple exercise. And how we do this equation? Well, it's very simple. So you can just write down the characteristic equation is r to the power 4 plus 5 times r to the power square plus 4. There's no r, right? So this is zero's derivative. This is zero's derivative. So that's kind of going to be just equal to 0. So that you can see that this is r squared plus 1. Okay, so multiplied by r squared plus 4 is equal to 0. That's going to give you r1 is equal to, okay, so let's say r1 is equal to I, r2 is equal to minus I, and r3 is equal to 2 times I, r4 is equal to minus 2 times I. So I'm going to have 4 solutions. And these are complex conjugate solutions. There's no repeatedness. So you can immediately construct the general solution is C1. So C1. So let me be more more precise in the first problem, right? So that R1 is equal to I is going to give you what? Well, R2 is equal to minus I. They're going to be giving you solutions y1, 2 are equal to what? Well, real part enters exponential. 0 is the real part multiplied by t. And then it's a cosine, right? So cosine of 1, so that's t, or e to the power 0 multiplied by t of sine t. So that basically, you're just going to create cosine t and sine t. So these are 2 solutions. Is that good, family? And what about R3 and R4? Well, they're equal to 2i and minus 2i. So that means you're going to create solutions y3, y4 is equal to cosine 2t and sine 2t. So that's going to be the solution. So these are the 4 fundamental solutions. Therefore, the general solution is just a linear combination c1 cosine t plus c2 sine t, right? So, and plus c3 cosine 2t plus c4 sine 2t. So that's going to be like your general solution. Is that good, family? Okay, so this kind of all this how these exercises are going on here. Okay, so let's look at some other equations. Okay, so what about this one? Can you find the general solution of this one? Y cubic derivative minus y first derivative, y is equal to 0, right? So again, you want to find a general solution. Okay, so you want to find a general solution. So how are we going to do this one? Well, the characteristic equation is r cubed minus 1 is equal to 0, right? So remember, y is corresponding to 1. So this is going to give you r minus 1 multiplied by r squared plus r plus 1 is equal to 0, right? So by standard factorization. So that r1 is equal to 1, r2 and r3 are equal to minus 1 plus minus square root of b squared minus 4ac is minus 3, right? So divided by 2a. So this is kind of going to give you minus 1/2 plus minus square root of 3 over 2 of I. Is that good, family? Where I is the imaginary unit. So that's being said, it means that the first solution is going to be y1 of t is e to the power of r1. This is a single root and it's real. So you just raise it to the power of t. r1 multiplied by t, r1 is 1. And for this one, you can see that lambda is equal to this, then mu is equal to this. So that means that we're going to create y2 and y3t is equal to e to the power minus 1/2 lambda of t. So lambda of t, and then cosinuses of square root of 3 over 2 multiplied by t, as well as e to the power of minus 1/2 of t of sinuses of square root of 2 multiplied by t. So that being said, that means the general solution is c1 e to the power of t plus c2 e to the power minus 1/2 of t multiplied by cosine square root of 3 over 2 of t multiplied by c3 e to the power minus 1/2 of t multiplied by sine square root of 3 over 2 of t. That's going to be the situation. Is that good, family? Okay, so that's kind of the exercise, so that you can actually practice. As I said, this class needs a lot of practice. Okay, so it is like an extension, natural extension of your calculus class. And in order to do well in such a class, you just need to practice as much as you can. Okay, so you just need to practice as much as you can. Okay, so if you want to be familiar with materials in this course, I would urge you to practice. Okay, so as much as you can do. Okay, so therefore we can continue this practice. Okay, so we can continue this practice. What about this one? Can you find a general solution of this equation? Okay, so of this equation. Okay, so this one. Okay, so let me say this equation. Okay, so let me say, let me put it here. Okay, so right, so I want to find a general solution of this one. So how about this one? Well, for this one, the characteristic equation is r cubed minus r squared minus r plus 1 is equal to 0. So now the problem, okay, so the problem here is that you don't really have any kind of quadratic formulas in order to find the roots, right? So in the higher order case, there's no exact quadratic formulas from which you can find the roots. So therefore, there you have to kind of resort to your high school mathematics. Okay, so you kind of have to resort to your high school mathematics. In the high school, we have been studying this kind of very important technique called factorization. That means you're giving me a polynomial. I want to factorize this polynomial. Factorization. How do we do factorization here? Well, the factorization is done via a method called grouping. So this is very important. You must grasp it. By grouping, it means, for example, I want to have r cubed minus r squared minus r plus 1 is equal to 0. How do I group? Well, I'm going to group the first two terms and group second two terms. So that's r squared of r minus 1 minus of r minus 1 is equal to 0. So that's going to have r squared minus 1 of r minus 1 is equal to 0. So that's representing this third order polynomial into the product is called factorization. So factorization is a kind of very important high school mathematics, but it is also very useful here. And therefore, you can do further factorization. R minus 1 is actually r plus 1, r minus 1, r minus 1 is equal to 0. So that means that the first root is minus 1, and the second is third root are repeated. They are equal to 1. So therefore, you want to construct the general solution, right? So let's say, can you go to the general solution, right? So let's say, can you go to the general solution immediately? Well, Immediately, we're going to see that y of t is C1. This single root is e to the power minus t. And then the double root are C2 e to the power of t plus C3. Then you're lacking solutions because these two solutions are repeated. So you have to be really alert here, right? So the solutions are repeated. So you want to insert t and raise everything to the e to the power of t. That's going to be your final general solution. Is that good for everybody? Okay, so this is how you create general solutions for such grouping method. Okay, so that's going to be that scenario. Let's continue our practice. Okay, so let's continue our quick practice. Okay, so for example, how about this one? Well, can you find a general solution of this equation? Okay, so fourth derivative. Okay, so let's say fourth derivative 4y double prime plus 4y is equal to 0. So I'm going to have this equation. Okay, so how am I going to practice this equation? Well, the characteristic equation again is r to the power of 4 plus 4 times r squared plus 4 is equal to 0. That's going to tell you r squared plus 2, you square it is equal to 0. So therefore, you can see that the roots are, okay, so the r1 is equal to, let's say, r2 is equal to square root of 2 multiplied by r. Because the I square is minus 1. Remember, I square is minus 1. So the R1, so R3 is equal to R4 is actually equal to its conjugacy minus square root of 2 of I. Is that good for everybody? Okay, so that means the roots are, complex roots are repeated, right? So for the first pair of complex roots, the real part is 0, complex part is square root of 2. So that you're going to see that the general solution, let me pass, okay? So let me pass to general solution immediately for now. Okay, so that means you have the first fundamental solution is e to the power of there's nothing because you don't have the real part. You don't need the e to the power. Then this is the cosinuses of square root of 2 of t, right? So plus the c2 of the sinuses of square root of 2 of t. These are corresponding to the square root of 2 of I and minus square root of 2 of I. However, if the roots are repeated, then you have to use the golden principle. So you're going to create C3 t times cosinuses of square root of 2 of t plus C4 t times the sinuses of square root of 2 of t. So that's going to be your scenario. You're going to insert t's in order to create a full spectrum of solutions. This is the, so you can see that the golden principle does not have to apply to exponential like t to the t multiplied by e to the power of rt. But it can also apply to complex root case. Is a good family. Okay, so that means that after this passing to the higher order equations, I would say the zoology of all the possible solutions in our spectrum becomes much more sophisticated, right? So there's actually a much better zoology about these solutions. Okay, so much more diverse zoology about these solutions. Okay, so as long as you have this, let's continue our practice. Okay, so let's continue our practice. What about this question? Okay, so can you find a general solution of this equation? Okay, so now we have a third order equation. Okay, so let me take this equation. Okay, so so we're going to have this equation. Okay, so it looks like something like this. Okay, so something like this. Then how are we going to deal with it? Well, you can see that the characteristic equations are cubed minus 3r squared plus 3 times r minus 1 is equal to 0. So now you can see again, it's like the grouping scenario what we've been talking about. It's a third order equation. Can you factorize it? Well, if you use the original idea of grouping, maybe you should group these two, you should group these two. Then you're going to have r squared of r minus 3 plus 3r minus 1 is 0. Then you have no idea how to deal with this scenario, right? So you don't know how to solve it. So that kind of grouping can sometimes be very technical. Okay, so the grouping can sometimes be rather technical. Okay, so how do we do this technical grouping? Well, what you're going to do is that you're going to group. Okay, so you're going to group this one with this one. So that means that's r cubed minus 1. And then it's minus 3 times r multiplied by r minus 1 is equal to 0. If you do this grouping, then you're going to have r minus 1, r squared plus r plus 1 minus 3r multiplied by r minus 1 is equal to 0. After this grouping, it becomes r minus 1 of r squared plus r plus 1 minus 3 times r. So that's going to give you r minus 1 multiplied by r squared minus 2r plus 1. So that's going to be r minus 1 cubic is equal to 0. Is that good, fam? Because this is actually r minus 1 squared. So that's going to be the how you do this grouping in this scenario. So that kind of looks a little bit weird, but remember you're grouping r cubed with minus 1, and then you're grouping 3r squared. Okay, so you're grouping 3r squared. So basically, what I'm saying here is that I group r cubed minus 1, and then let's group minus 3r squared plus 3r is equal to 0. And the good thing here is that you can factorize this 3r out of this formula, and then you have r cubed minus 1 can also factorize r minus 1, and there are two common r minus 1s, which means you're successful in the grouping. So that means the characteristic roots are actually all equal to each other. R1 is equal to R2 is equal to R3 is equal to 1. In that case, if you want to have a solution, then the solution, okay, so if this grouping, if you do the grouping in this way, then you're going to be happy, right? So that's going to be the good grouping. Now it means that the solution is repeated 3 times. It's just one root. So the first one will be e to the power of t, no problem. And starting from the second solution, you should use golden principle. But you're still, you can continue the golden principle because it is repeated 3 times. You want to create a spectrum solution that matches the number of repeatedness. So that C3 is t squared e to the power of t. That's going to be the scenario. Is that good, family? Okay, so that's kind of the scenario, how you're going to practice this type of problems. There are many exercises that I have suggested in this section that you need to, as I said, you need to practice in order to get yourself truly familiar with this method. Okay, so that's what we would like to have for the homogeneous equations, right? So what happens to the non-homogeneous equation? Well, if you come back to the theory that we've been talking about in this lecture, it's if you have non-homogeneous equations, right? So if you have non-homogeneous equations, then the solution theory is going to be something like this. So if you have a(n) of t, let's say y(n)'s derivative plus dot 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 plus a1 of t, okay, so of y prime plus a0 of t of y is equal to b of t. So that's going to be a non-homogeneous equation. Okay, so let's say non-homogeneous equation. If you have such non-homogeneous equation, then what you're going to do is that you're going to create the complementary, right? So let's say the complementary solution. Okay, so the complementary solution is a(n). Okay, so a(n) of t of yc of the n's derivative plus a0 of t of the yc is equal to 0. Complementary, and the complementary solution is yc of t is c1 y1 of t plus dot 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 plus cn yn of t. So that's going to be complementary solution. But from the complementary solution, you also need a particular solution, right? So you also need a particular solution. Particular solution satisfies the non-homogeneous equation. So that means a(n) of t yn's derivative plus dot 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 plus a0 of t of y is equal to b of t. So you will need this particular solution. And therefore, once you have the complementary and the particular solution, the general solution is just equal to y of t is equal to the complementary solution plus the particular solution. That's it. You just need to find one particular solution in order to create a general solution for the non-homogeneous problem. That's kind of the general theory that we've been talking about before. Is that good, family? Right? So it's a natural extension of the general theory that we've been talking about before. So the key point here is how do you find this particular solution, right? So how are you going to find this particular solution, which is here? So now previously, if the equation is the second order, right? So in the second order equation case, we've been considering two different methods of finding the particular solution. One method is called the method of undetermined coefficients. Right, so that's the method of undetermined coefficients. By method of undetermined coefficients, it means that you're going to look at the right-hand side b and look at the shape of the b. If the b is exponential, you're going to try exponential with some unknown coefficient. And if sine and cosine, you try sine and cosine. If polynomial, you try polynomial. Maybe the mixture of them, then you try mixture. So this is called method of undetermined coefficients. Is that good, family? Okay. The other method is called variation of parameters. Okay. So the other method is called variation of parameters. By variation of parameters is a more general method. It happens if even if the B is not in the standard, like the elementary function, but it's more general. Then you're going to construct the Wronskians. There are formulas for the variation of parameters. You're going to vary those C's into parameters, etc., etc. Right? So, however, here for this lecture, we're going to just talk about the method of undetermined coefficients for higher order equation. Okay, because the variation of parameters for higher order equation involves the Wronskian calculation that might be too complicated for this lecture. So we're going to kind of focus on this method. Okay, so we're going to focus on this method. So how does the method of undetermined coefficient goes? Okay, so how does this method of undetermined coefficient goes? Right. So let me review this method of undetermined coefficients. So basically, it is an idea that you're going to guess as a particular solution. How do you guess the particular solution? Well, if you have an exponential function, you should try an exponential function with some coefficients in front of it, right? So you should try an exponential function with some coefficients in front of it, right? So that's one scenario. Okay, so that's one scenario. Now, if you have sine and cosine, okay, so no matter it is sine or cosine, you're going to try a linear combination of sine and cosine, right? So no matter it is sine or cosine, you should try a linear combination of sine and cosine. So that's going to be another scenario. Now, if you have a polynomial function of order n, then you should try a polynomial function of the same order. Okay, so that's kind of the key idea that for polynomial functions, you should always try polynomial functions of the same order. Okay, so you should always try polynomial functions of the same order. And then the last scenario is that if the initial assumption of capital Y of t has been overlapped with part of the complementary solution, so this is another place where you have golden principle, right? So if your initial assumption of the particular solution, that means the particular solution has overlapping part with the complementary solution, then you're going to keep multiplying it by t until it is not overlapped with any part of the complementary solution, right? So we're going to keep multiplying by t until, so that's another place where the golden principle has been applied. Okay, so we'll see examples just to remind you what this is if you forgot about this scenario, but here is a summary. Okay, so that's kind of about this. And then we've been talking about like the principles of divide and conquer, which means that if you have a product of the above three types of right-hand side function, then you assume that capital Y of t is the product of the corresponding particular solutions, right? So this is about products. And if there is summation, then again, you have to divide this summation into each of this, decompose it in each of the parts, and then work out the particular solution for each term in the summation and add all of them. So that's kind of, these two are the so-called divide and conquer principle, right? So, and this one is about the golden principle, and there's three basic principles that has been discussed here. Okay, so these are kind of just to remind you what happens. Okay, so what happens to this method of undetermined coefficients, but we need exercises. Okay, so let's say method of undetermined coefficients. Okay, so method of undetermined coefficients. Okay, so that means we need to have more exercises. Okay, so let's start our practice. Okay, so let's start our adventure on exercises. Okay, so let's first look at this one. Okay, so can you find a general solution of this equation? Okay, so can you find a general solution of this equation? Okay, so let me put it here. Okay, so okay, so we want to find the general solution of this equation, right? So how are we going to do that? Well, the idea, okay, so the idea here is that we're going to consider the characteristic equation first. R to the power 4 plus 5 times r squared plus 4 is equal to 0. This is actually the equation that we've been considering before, right? So that was this example was this one, right? So this we already constructed its fundamental solutions. So therefore, you really do have this idea, right? So you do have this idea. So let me just take it, right? So this is actually the complementary equation because we just removed the right-hand side, right? So the left-hand side is the same equation. So therefore, the fundamental solutions are already constructed, right? So fundamental solutions are already constructed, right? So they're already constructed so that we can just make use of them here, right? So this is going to be the fundamental solution. Okay, so it's going to be the fundamental solution. So therefore, I'm going to say that this is the YC of T. Is that good for everybody? Okay, so this is going to be the fundamental solution. Now, as long as you have the fundamental solution, you want to find a particular solution. So that means y fourth derivative plus 5 times y second derivative plus 4 times y is equal to 8 times t squared plus t. Remember, it has to be the non-homogeneous equation. How do you find a solution? Well, you're going to try a particular solution, y of t. As we said, this is a polynomial. So you should try a polynomial. But what's the order of the polynomial? Well, our principle is saying that you should try a polynomial of the same order. So that means it should be at squared plus b times t plus c. You cannot try third order or first order. It has to be like the same order here. And therefore, you just have to take derivatives. However, this type of problems can sometimes be pretty tedious because you have to take a lot of derivatives, right? So that means you see you have second and fourth derivative, so that's not enough. So y prime is equal to 2at plus b, and y double prime, that's the second derivative, that's 2 times a. And starting from the third derivative and the fourth derivative, they're both equal to 0. Is that good, family? As long as you have all that, it means that y fourth derivative plus 5 times y second derivative plus 4 times y is equal to what? Is 0 plus 5 times second derivative is 2 times a plus 4 times that's at squared plus b of t plus c. So you're going to have this. Now, once you have this, it means that you're going to have 4a of t squared plus 4b. Okay, so 4b of t plus 4c plus 10 times a. That's going to be the polynomial. And this polynomial is 8t squared plus, okay, t, and there's 0 here. So that you can see that from here, you're going to be able to solve this ABC, right? So basically, it means a is equal to 2 because 4a is 8 and 4b is 1. So that means b is equal to 1 over 4, right? So, and what about the c? Well, c is equal to 4c plus 10a is 0. So maybe we're going to see that 4c. Okay, so let me put it above. Okay, so that 4c plus 10 times a is equal to 0, which means that 4c plus 20 is equal to 0. C is equal to minus 5. As long as you have the ABC, you get the solution. Capital Y of t should be equal to what? Well, it's equal to 2t squared plus 1/4 of t and minus 5. And that's going to be the particular solution. Now, as long as you have the particular solution, you have the general solution. Okay, so the general solution, right? So the general solution is going to be just equal to the complementary solution plus the particular solution. Is that good, family? Okay, so do you remember the complementary solution? It was C1 cosine, C2 sine. Okay, so that's the C1 cosinesis of t plus C2 sinesis of t plus C3 cosinesis of 2t, right? So plus C4 sinesis of 2t, right? So, and then plus the particular solution is 2t squared plus 1 over 4 of t and minus 5. So that's going to be how you find the general solution. Is that good, family? Okay, so that's going to be the scenario. Okay, so that's going to be the scenario. Is that good, family? Okay, so let me continue. Okay, so we're going to continue this practice. Okay, so let me see how many examples I do have. Okay, so there's going to be one more example. Okay, so let's see. Okay, so maybe let me stop the lecture here today. Okay, so And then we're going to continue with practicing some more problems in the next lecture. Okay, so let me stop the lecture today. Okay, so and we're going to continue the lecture in the next lecture. Okay, so and so much for today.